Humanity stands on the threshold of a new era, an era defined not only by exploration, but also by the bold dream of colonization. For decades, our gaze has been fixed on the familiar: the Moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-trodden paths lies a world shrouded in mystery, a world that's changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered with a dense atmosphere, which is rare for a moon. It's a place where rivers and lakes flow not with water, but with liquid methane and ethane. Here, the sky is raining gasoline. And the cold is beyond anything that can be experienced on Earth. Yet, in this alien landscape lurks the potential for something extraordinary. Could Titan, a world so unlike our own, hold the key to our future in space? Could this distant moon hold the secrets to not only surviving, but thriving beyond our home planet?
It's one small step for man, one giant leap for mankind.
As we turn the pages of our history of space exploration, the Moon and Mars become beacons of human ambition. The Moon, our nearest celestial neighbor, has always been a constant companion in our night sky, a symbol of our desire to leave the confines of the planet. Mars, in turn, with its striking resemblance to Earth, fuels our dreams of finding a new home in space. Nevertheless, the Moon, despite its proximity, presents serious problems. Its surface is a barren wasteland, devoid of atmosphere and offering no protection from the harshness of space. The lunar environment is a vacuum, exposing astronauts to extreme temperatures and cosmic radiation. No atmosphere means no air to breathe, no wind to carry sound, and no sky to protect against the relentless barrage of solar and cosmic rays. Mars, though more Earth-like, is not without its own problems. Its thin atmosphere, consisting mostly of carbon dioxide, offers little protection from solar and cosmic radiation. The Martian environment is harsh and merciless, and temperatures at the poles can drop to minus 257 degrees Fahrenheit. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, Saturn's largest satellite, presents a very different environment. Shrouded in a dense atmosphere, Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than even the Earth's atmosphere, is the key to protecting future colonists from cosmic rays that mercilessly bombard less protected worlds such as the Moon and Mars. Titan's atmosphere isn't just a shield, it's a gateway to opportunity. Unlike the Moon and Mars, the air pressure on Titan's surface is 1.5 times higher than on Earth, creating a surprisingly familiar pressure environment for human explorers. This dense atmosphere opens up new possibilities for exploration and colonization, possibilities that are beyond the reach of our more trivial space goals. As we rethink our goals for space colonization, Titan becomes a compelling alternative, a world in which the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become its strengths. Titan invites us to envision a future in which humanity can thrive under the protective embrace of an alien sky. A future in which the mysteries of this distant moon become stepping stones to our expansion into space. As we mentioned earlier, Titan, a moon of many mysteries, orbits around Saturn. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan has captivated the imagination of scientists and dreamers ever since. This world is both similar to and in stark contrast to our Earth. Titan's environment is unlike anything else we've encountered in our solar system. It's the only known moon with a dense atmosphere, and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it's not just the size that makes Titan stand out, it's the rich composition of its atmosphere and surface that really sets it apart. This moon is surrounded by a thick, nitrogen-rich atmosphere, similar in composition to Earth's, but far denser and more extensive. It's permeated with organic molecules, creating a kind of hazy orange glow that obscures the surface of the satellite from view. It's this nitrogen-dominated atmosphere that provides protection from solar radiation, which contrasts sharply with the barren sky of the Moon and Mars. Beneath this alien sky lies a landscape at once familiar and utterly alien. Titan's surface is formed by rivers and lakes, but they're not bodies of water as we know them. Instead, they're filled with liquid methane and ethane, flowing through channels carved into the Moon's icy crust. These hydrocarbon seas are a true marvel, a testament to the diversity of the universe's chemistry. The presence of these surface fluids is a key characteristic that distinguishes Titan from other celestial bodies. On Earth, the water cycle shapes climate and geography. On Titan, a similar cycle occurs, but the role of water is played by methane and ethane. This hydrocarbon cycle, with methane rain and ethane lakes, creates a dynamic environment that may provide clues to understanding the complexity of planetary atmospheres. So, by breaking the limits of our standard perception, we're slowly uncovering exactly what makes a planet or moon habitable. Its nitrogen-rich atmosphere and surface fluids open the door to new possibilities. Let's find out what they are. So the Moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, a major challenge for space colonization. Why do we pay so much attention to solar radiation? Well, the answer is simple, yet profoundly important. Solar radiation is a ruthless destroyer of living cells. It doesn't just affect microscopic life forms, it directly affects us as human beings. Unshielded exposure to solar radiation can cause severe cellular damage, destroying the very fabric of our biological existence. In space, spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts. On Earth, it's the atmosphere and magnetic field that protect us. On Titan, it's the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the barren landscapes of the Moon or Mars. Beneath this protective dome is a world of liquid methane and ethane. These hydrocarbon lakes and rivers stand in stark contrast to the bodies of water we know on Earth, yet they offer intriguing possibilities. Imagine a world where boats sail on methane seas, where the familiar concept of the liquid cycle takes on a whole new form. The presence of these surface fluids is not just a curiosity, it's a resource. Methane and ethane have the potential to be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to one of the biggest problems of space habitation: sustainable energy sources. But Titan's gifts don't end there. Beneath its icy surface lies another treasure: water ice. The very water so essential to human life is abundant on the satellite, trapped in its frozen crust. The presence of water ice, along with hydrocarbons, makes this moon a repository of vital resources, setting the stage for a self-sustaining human presence away from Earth. Titan, a world of incalculable potential, also presents enormous challenges. Severe cold, during which temperatures drop to minus 356 degrees Fahrenheit, creates an environment unsuitable for human life as we know it. In turn, methane rain, a phenomenon unique to this moon, adds another layer of complexity to the survival equation. To overcome these challenges, we must turn to the pinnacle of human ingenuity and technology. Colonizing Titan will require not just adaptation, but a complete rethinking of human habitation in extreme conditions. Imagine dwellings designed to withstand low temperatures, insulated with materials yet to be invented, and harnessing the power of Titan's own resources to provide warmth and comfort. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem itself into a resource for solving it. But survival is more than just keeping warm. Methane rain, while an obstacle, could turn into an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as a raw material for essential commodities. Now, let's imagine a human colony on Titan. Imagine domed cities, their architecture a blend of science and art, designed to harmonize with Titan's unique environment. These structures, resistant to cold and methane rains, would be interconnected, forming a network, demonstrating human resilience in the face of alien conditions. Inside these domes, life thrives. Hydroponic gardens provide food, recycling systems conserve resources, and public areas foster a sense of community. It's a place where humanity has not just survived, but flourished, adapting decisively to Titan's challenges. Colonizing Titan is not just a distant dream, it's a future that beckons us to take up the challenge. With each technological breakthrough, with each bold leap of imagination, we come closer to making this alien world a new home for humanity. Watching the thriving human colony on Titan, it becomes clear that this moon is more than just a new home for humanity. It's a center of economic and scientific opportunity. The unique environment and abundant resources offer unprecedented prospects for both. The economic benefits of colonizing Titan are rooted in its vast hydrocarbon reserves. Key components of Titan's lakes and atmosphere are not only potential sources of energy, but also valuable raw materials for chemical synthesis. The ability to harness these resources could turn Titan into an economic center, meeting both the colony's needs and potentially supplying materials for interplanetary trade. Scientifically, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that offer insights into organic chemistry and astrobiology. Studying Titan's methane cycle and its prebiotic chemistry could unlock the secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. Moreover, Titan's position in the solar system and its resources make it an ideal launching pad for future space exploration. Its low gravity and abundant fuel reserves could make it easier to launch spacecraft to distant destinations, making Titan a strategic outpost for exploring the outer solar system and beyond. However, with these opportunities come important ethical considerations. As we embark on the colonization of Titan, we must reflect on our responsibilities in interacting with the new world. Conservation of Titan's environment, respect for its unique characteristics, and thoughtful stewardship are paramount. We must approach Titan not as conquerors, but as custodians. How we relate to this world in the future will reflect our values and our ability to balance progress and responsibility. As we conclude our journey, let's reflect on the key points. A moon once shrouded in mystery has turned out to be a world full of potential. We explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We traveled through alien landscapes where rivers and lakes of methane and ethane cut through icy terrain, offering resources that could secure our future in space. Our journey also took us to the potential of a vibrant human habitat, where ingenuity and resilience have turned challenges into opportunities. We saw how Titan's economy, driven by its abundant resources, can be a cornerstone of our interplanetary endeavors. As we ponder the future of humanity on Titan, we're reminded that colonization is not just about achieving technological perfection. It's a journey that forces us to grow, learn, and respect the universe we live in. So we leave you with a great question. What does this step mean for the future of humanity? How will our efforts on this distant moon affect our destiny in the vast, uncharted expanse of space? There are countless untold stories in the universe, but one mystery veiled in the shadows of distant suns stands out prominently among many others. This discovery invites us to look beyond earthly boundaries and ponder untold possibilities. This is the story of Kepler 22b, a planet that's not just wandering in the void, but basking in the sweet spot, its star's habitable zone. Here, in this delicate balance, all conditions exist to ignite the magic of life, for the water to flow freely and the atmosphere to hold the secrets of existence. Discovered by the gaze of the Kepler Space Telescope, Kepler 22b invites us to ponder what worlds may lie beyond our own, to question our understanding of life and our role in the universe. It makes us dream of new horizons, of distant shores where humanity may one day set foot. Today we'll embark on a journey of discovery to unravel the mysteries of Kepler 22b and the countless other worlds that await us beyond our reach in the limitless expanse of space. In its search for Earth analogs scattered throughout the galaxy, the Kepler Space Telescope has become a pioneer, a celestial cartographer mapping the unknown. Initially, Kepler's mission was very clear: to observe the vastness of the Milky Way, looking for the faint twinkle of stars dimmed by the passing of planets in their orbit. Equipped with the most sensitive photometers, the telescope patiently watched the light of more than 150,000 stars. Among them, a pattern emerged: the rhythmic fadings of a particular star, not unlike our Sun. This was the first hint of Kepler 22b, a planet moving carefully around its star and briefly eclipsing its light, as if playing cosmic hide-and-seek. This discovery was a real event. The analytical skill required to sift through huge datasets and pick out planetary transits from the cacophony of cosmic noise was immense. It was akin to detecting a faint brightness difference caused by a moth flying in front of a lighthouse beam from thousands of miles away. The method of transits, Kepler's main tool, is a deceptively simple but very powerful technique. This method is based on the subtle interactions of planets orbiting their stars, passing in front of them for a moment and casting a small shadow, which then causes a slight dimming of the star's light. It's this faint, fleeting shadow that astronomers look for, a sure sign of a distant world orbiting its star. The elegance of the transit method lies in its simplicity and the wealth of information it provides. When a planet passes in front of its star, it blocks some of the starlight, causing a measurable dip in brightness. This dip, detected by instruments such as the Kepler photometer, is carefully analyzed to reveal not only the presence of the planet, but also its size. The amount of obscured light tells us how large a planet is compared to its star. Moreover, the regularity of these brightness variations reveals the planet's orbital period, the time it takes to complete one orbit around its star. This rhythm of disappearance and reappearance allows scientists to calculate how far away a planet is from its star, which provides crucial information about the planet's environment and its probability of habitation. This method also opens a window into the planet's atmosphere. When a star's light passes through a planet's atmosphere during transit, certain wavelengths of light are absorbed by atmospheric gases. By studying these changes in the star's spectrum, astronomers can determine the chemical composition of the planet's atmosphere, finding fingerprints of molecules that may indicate the presence of water, oxygen, or even signs of biological activity. The discovery of Kepler 22b was a watershed moment in the search for Earth analogs. It highlighted the incredible potential of our technology and the perseverance of scientists. This discovery has moved us further along the path of space exploration, opening new chapters in the history of the search for worlds that could one day become a second home for humanity. In the variety of cosmic interactions between planets and stars, there is a delicate region, a narrow band where conditions are just perfect. where the hope of life as we know it lingers in the darkness. This region, known as the habitable zone, is a cradle for potential life. A haven where water can exist in a liquid state, neither boiling under the fierce light of a star, nor freezing in the cold expanse of space. Imagine a world very similar to our Earth, located inside this life-supporting belt. Here, the heat from the star is neither too intense nor too weak, bathing the planet in soft light. And this is where Kepler-22b is, orbiting serenely in the habitable zone of its star, a prime candidate in the search for Earth-like conditions and possibly life beyond our solar system. Just as Earth thrives in the Sun's habitable zone, Kepler-22b enjoys a similar privilege, orbiting at a distance where temperatures can allow lakes, rivers, and oceans to exist. The presence of liquid water, the universal solvent of many chemicals, is crucial, for it is in water that the chemistry of life unfolds. Water is the stage on which the drama of life is played out, from the simplest bacteria to the most complex forms of flora and fauna. Yet only the presence of water in a liquid state is one of the many conditions necessary to sustain life. What have we learned from analyzing this distant world? And is it so open to the theoretical presence of humans on it? As we dive into the mysteries of Kepler-22b, we embark on a journey of discovery, piecing together the puzzle of this distant world through the lens of our own Earth. With each observation, scientists are getting closer to understanding the fundamental nature of this distant planet, its size, its composition, and the very air that surrounds it. It's these factors that will help shed light on the presence of the basic components that may make this distant world a cradle for life. So, what are these factors? At the forefront of the search for life is, of course, the presence of liquid water, the cornerstone for all known biological processes on Earth. As we already know, Kepler-22b, which occupies a privileged position in the habitable zone, receives from its star a flow of energy that suggests that the temperature may be favorable for maintaining water in a liquid state. While the presence of liquid water is a promising start, the composition and behavior of Kepler-22b's atmosphere remains crucially unknown. Enveloping the planet, the atmosphere is the most important determinant of environmental conditions affecting temperature and surface pressure. Because the planet is in the habitable zone of its star, the theoretical presence of an atmosphere similar in composition to Earth's, rich in nitrogen and containing the requisite amount of oxygen and trace gases, could mean a temperate climate and stable water cycles similar to those that have nourished life on our home planet for billions of years. However, the range of possible atmospheric scenarios is enormous and shrouded in uncertainty due to our current technological limitations in directly observing exoplanet atmospheres at such great distances. If Kepler-22b's atmosphere tends toward a denser, carbon dioxide-dominated composition like that of Venus, this could lead to a greenhouse effect. In such a scenario, any potential water would exist as supercritical vapor at extreme pressures and temperatures. Conversely, an atmosphere that's too thin and free of greenhouse gases could turn Kepler-22b into a frigid world where water exists only as ice and the surface is exposed to harmful cosmic radiation. The equilibrium temperature of the planet, estimated at a comfortable 72 degrees Fahrenheit under Earth-like atmospheric conditions, indicates the possibility of an environment with ideal conditions for Earth-like life. However, if one were to go to the other extreme and create a Venus-like greenhouse effect, the surface temperature could soar to a scorching 860 degrees Fahrenheit, which would likely preclude the existence of life as we know it. Things get even more complicated. The elemental recipe for life goes beyond just water and the right atmosphere. Life, as we know it, is intricately woven from a variety of chemical elements, with carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur playing major roles. Sun-like stars, including Kepler-22, are G-type stars and typically have similar proportions of hydrogen and helium, with a small amount of heavier elements playing a primary role. However, during planetary system formation, the distribution and concentration of materials in the protoplanetary disk around the nascent star influence the further composition of the forming planets. Temperature gradients in this disk lead to condensation of different materials at different distances from the star, which affects the composition of the planets. Once a planet is formed, its composition can be altered by differentiation, the separation of different materials within the planet, resulting in the formation of distinct layers, such as the core, mantle, and crust, and geologic processes such as volcanic activity and plate tectonics. So while direct measurements of the chemical composition of Kepler-22b are beyond our capabilities, the diversity of elements in the universe and the planet's location in a habitable zone can only hint at the exciting possibility of the presence of the building blocks that create the basis for the complex chemistry of life. While we wonder whether the planet's atmosphere might contain a protective layer like ours, or whether it's a dense, oppressive cloak trapping heat as a result of the greenhouse effect, and what the planet's chemical composition actually is, one thing we know for sure: the last, fourth parameter necessary for life is in almost perfect agreement. The complexity of life must necessarily be fueled by energy, and the presence of Kepler-22b in the habitable zone ensures its constant supply from the host star. This energy, which powers photosynthesis on Earth, could drive the fundamental biological processes necessary for life on this distant planet. The characteristics of a star that is slightly cooler and smaller than our Sun, but similar in many ways, provides a stable source of light and heat. Against the grand landscape of the cosmos, Kepler-22b stands out as a beacon of possibility, a world where the basic ingredients for life as we know it can come together. Yet the true nature of this distant planet remains shrouded in mystery, reminding us of the vast unknowns that await us as we continue to search for the secrets of the universe and the potential for life beyond our solar system. The search for signs of extraterrestrial life is the cornerstone of our celestial explorations, compelling us to venture into the unknown with hope and scientific rigor. As we turn our eyes toward distant worlds like Kepler-22b, the next generation of telescopes and space missions are poised to pierce the cosmic veil, inviting us to peer into the atmospheres of these distant planets and learn their secrets. At the forefront of this cosmic quest is the James Webb Space Telescope, the most sophisticated and powerful space telescope ever built. With unprecedented resolution and sensitivity, the JWST is designed to observe the universe in the infrared, enabling it to detect the faint reflections of light from the earliest stars and galaxies and, crucially, the atmospheric signatures of exoplanets. The JWST suite of instruments carefully analyzes light passing through the atmosphere of exoplanets as they transit their host stars. This process, known as transmission spectroscopy, will allow scientists to decipher the composition of the atmospheres of these worlds in search of characteristic signatures of molecules essential for life, such as water vapor, oxygen, and methane. The mission of the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018 and complementing JWST, is to survey the brightest stars near Earth for transiting exoplanets. Building on the legacy of the Kepler mission, TESS is casting a wider net, revealing many new worlds for further study. Among them, planets that share characteristics with Kepler-22b will be prime targets for detailed atmospheric analysis, opening up new opportunities to search for biosignatures. Coming down to Earth, the Extremely Large Telescope, or ELT, which, when completed, will be the world's largest optical telescope, will be another powerful tool in the search for alien life. The ELT's colossal mirror located atop Cerro Armazones in Chile's Atacama Desert. We'll collect light from distant exoplanets, allowing direct images and spectroscopic studies of their atmospheres. Its advanced instruments will be able to detect even the faintest chemical fingerprints, further expanding our understanding of such distant worlds. Looking ahead, proposed missions such as the Habitable Exoplanet Observatory, HABEX, and the Large UV Optical IR Surveyor, LUVOIR, promise to push the boundaries of exoplanet research even further. Equipped with advanced technology such as coronagraphs and star shades, these observatories aim to directly image exoplanets by dissecting their light to reveal the molecular composition of their atmospheres in unprecedented detail. The hunt for alien life embodied in exploring such planets continues to inspire and stimulate the human spirit, reminding us that the search for life beyond Earth is more than just a scientific endeavor. It's a profound exploration of our place in the cosmos. As we stand on the threshold of discovery, our thoughts drift to the distant world of Kepler-22b, a planet in the nourishing embrace of its star's habitable zone. Here, in this hypothetical realm, we imagine the possibilities such a world might hold. Could it be that the hilly landscapes of this distant planet are home to a diversity of alien flora thriving in the soft light of Kepler-22? Could it also be that its seas are teeming with life, with forms both strange and outlandish, adapted to the unique conditions of this distant world? And what is humanity's potential role in such a world? For now, it's hard to imagine, but these dreams are underpinned by the relentless pursuit of knowledge that defines our current path in exoplanet exploration. As we gaze into the heavens with instruments such as the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the upcoming Extremely Large Telescope, we continue to push the boundaries of our understanding. Each discovery adds its own piece to the great puzzle of the cosmos, revealing the diversity of worlds that inhabit our galactic neighborhood. The future of exoplanet exploration promises to deepen our understanding and knowledge of distant worlds and redefine our place in the universe. As we stand at this crossroads of imagination and discovery, we remind ourselves that the search for life beyond Earth and the understanding of humanity's future potential among the stars is a reflection of our deepest desires to explore, understand, and reconnect with the vast, wondrous cosmos that is our home. In the vast, silent expanse of our solar system, beyond the familiar brilliance of Neptune, rumors of some unseen presence have been stirring astronomers for quite a few years now. This mysterious force, unseen but undeniable, stretches the very fabric of our cosmic neighborhood, bending the paths of distant objects with its invisible grip. Here in the shadowy depths of space, where the warmth of the sun barely reaches, lies a mystery that's baffled the brightest minds. The hypothetical world known only as Planet 9, whose existence can be determined not by direct observation, but only by the subtle interaction of trans-Neptunian objects performing complex orbital motion. Could there be a rogue planet, shrouded in the darkness of space, exerting its influence from afar? A world that defies our understanding and challenges the very limits of what we know about our solar system. Join us as we piece together clues scattered in the back of the solar system in search of a planet that has so far eluded our sight. In the early 1990s, the outer reaches of our solar system began to reveal their secrets. Astronomers discovered a region teeming with icy bodies, now known as the Kuiper Belt. This discovery marked the beginning of a new chapter in our cosmic journey, expanding our understanding of the boundaries of the solar system. Among these distant wanderers was Pluto, long considered the ninth planet and proudly bearing that title since its discovery in 1930. But as the Kuiper Belt uncovered its treasures, Pluto's status began to be questioned. The discovery of objects such as Eris that rivaled and even surpassed Pluto in size sparked a debate that shook the foundations of planetary classification. In 2006, the International Astronomical Union was faced with an unresolved situation. What defines a planet? The answer to this question led to a controversial decision that downgraded Pluto to a dwarf planet. This decision, met with both approval and opposition, has swept through the astronomical community and the public, redefining the way we think about the solar system. In this cosmic controversy, however, the seeds of a new mystery were sown: the peculiar orbits of some Kuiper Belt objects, including the then distant newly discovered Sedna, hinted at an invisible influence from the shadows guiding these icy bodies. Could it be that another planet, hidden in the vastness of space, created the architecture of the outer solar system? This question ignited the imagination of astronomers like Mike Brown and Konstantin Batygin, who set out to find the truth. Their journey will lead them to speculate on the existence of Planet 9, a hypothetical world hiding behind Neptune, whose presence is signaled only by the interaction of the most distant members of the Kuiper Belt. A new planet emerging from the heart of controversy awaits discovery. As we move beyond the familiar boundaries of the inner solar system, a realm of icy bodies and distant orbits opens up before us. Here, in the cold, dark regions beyond Neptune, lies an enigma that has captivated astronomers for years. It's the Kuiper Belt, a vast ring of debris left over from the formation of the solar system. Among these celestial wanderers, a separate group shows peculiar behavior that contradicts the expected norms of orbital mechanics. These are detached TNOs, or trans-Neptunian objects, whose paths are free of Neptune's gravitational influence, and extreme trans-Neptunian objects, or ETNOs, whose orbits are so eccentric that they seem to be tethered to some invisible force. What could be the architect of this unusual behavior? The answer may lie in the gravitational anomalies that pervade this distant region. These anomalies, subtle but deep, indicate the presence of a massive object whose gravitational pull shapes the orbits of these distant objects. The detached TNOs, whose orbits seem to be unaffected by Neptune, hint at a disturbance in the gravitational harmony of the outer solar system. Meanwhile, ETNOs, with their extreme orbits, paint a picture of cosmic interaction guided by a hidden force. The quest to understand these gravitational mysteries led researchers to hypothesize the existence of Planet 9, a hypothetical world whose mass and orbit could explain these anomalies. By carefully mapping the orbits of these mysterious objects, scientists began piecing together the potential location and characteristics of this invisible planet. In the tranquil balance of our solar system, each planet plays its part, revolving around the sun in a centuries and centuries and centuries old rhythm. But beyond this familiar rhythm looms a shadowy figure, a silent participant whose presence is felt but not seen. Let's take a closer look at the Planet 9 hypothesis itself. In 2014, astronomers Chad Trujillo and Scott S. Shepard noted an intriguing similarity between the orbits of Sedna, 2012 VP-113, and several other ETNOs, a phenomenon too unusual to be a mere coincidence. Trujillo and Shepard made a bold suggestion: the existence of an unknown planet whose orbit is a perfect circle between 200 and 300 astronomical units from the Sun. A few years later, in 2016, Mike Brown and Konstantin Batygin embarked on an intellectual journey delving into the mysteries of the outer solar system in order to develop this hypothesis. Through careful analysis and computational modeling, Brown and Batygin pieced together previously found gravitational anomalies that indicated the existence of a massive invisible planet. This hypothetical world, in their opinion, could be the key to unraveling the special dynamics of the outer part of the solar system. As their research progressed, so did their understanding of the potential characteristics of Planet 9. Its mass was originally thought to be 10 times that of Earth, but further research revealed that its mass was slightly less, but still significant at about 5 or 6 Earth masses. This revision painted a picture of a planet powerful enough to control the orbits of distant objects, yet elusive enough to remain hidden from our most powerful telescopes. The influence of this hypothetical planet extends far beyond its immediate vicinity. Its gravitational influence can explain the clustering of the orbits of detached TNOs and the extreme trajectories of ETNOs, weaving together a complex picture of celestial mechanics. The hypothesis of Planet 9 sparked a flurry of scientific research, and astronomers around the world joined the hunt for this elusive neighbor. The search for Planet 9 is a journey fraught with difficulty, a testament to both the vastness of the universe and the limitations of our current technological capabilities. Its distant orbit, presumably huge and elliptical, leads it through the farthest reaches of our system. This region, where the light of the sun is almost unattainable, envelops the planet in total darkness. This remoteness poses a serious problem because the potential position of the planet can encompass vast portions of the sky, requiring extensive, focused searches covering these celestial expanses in painstaking detail. It's something akin to trying to find a needle in an astronomical haystack. Moreover, because of its distance from the sun, the planet's surface temperature is extremely low, meaning it emits minimal thermal radiation, making infrared detection just as difficult. The lack of emitted and reflected light is compounded by the glare of distant stars and the myriad cosmic objects that fill the sky, each vying for the attention of our telescopes. Among other difficulties, the nature of the search is compounded by the planet's enormous orbital period, which is thought to be thousands of years. Because the planet's motion across the sky is imperceptibly slow from our earthly perspective. Even after a decade, Planet 9's position in space will have changed only slightly, making any attempt to observe its motion in the short term virtually impossible. This chilling rate of motion means that traditional methods of detecting planets by observing their transit or motion against the background of stars are not feasible. However, in their relentless pursuit, astronomers use an array of sophisticated techniques and instruments, from ground-based telescopes equipped with advanced adaptive optics to space-based observatories that circumvent the Earth's atmospheric distortions. So, in the pursuit of Planet 9, astronomers have had to go beyond traditional observational methods, leading to the development of several innovative approaches aimed at refining the elusive planet's location. They utilize unique aspects of the solar system's external environment and potential celestial interactions that Planet 9 may have with other objects. One of the proposed approaches has to do with potential moons that may orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes internal heat to be released within the moon, potentially making it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid subsurface oceans and also provokes vigorous volcanic activity on Io. This internal heating may cause the moons to emit infrared radiation more perceptively than Planet 9 itself, providing an indirect but promising avenue for detection. Another innovative method involves tracking the trajectories of interstellar asteroids passing through our solar system. These high-speed objects, coming from regions outside our solar system, could potentially be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational jolts it exerts on passing bodies. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose path through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft passing through the outer solar system can also provide valuable insights. Like asteroids, when spacecraft travel vast distances between planets, their trajectories are slightly and subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unaccounted gravitational anomalies that may hint at the presence of Planet 9. This method requires accumulating huge amounts of data over long periods because the gravitational effects are incredibly subtle. However, the results can be very significant and will pay off the time spent. Moving from direct observation to indirect detection through a planet's influence on its environment may be the key to unlocking one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also spawned many theories and speculations about the true nature of this elusive object. Among the most intriguing are hypotheses that Planet 9 could be a primordial black hole or a dense dark matter clump, each representing a radical departure from the traditional planetary view. The idea that Planet 9 could be a primordial black hole introduces a sharp twist to the narrative. Unlike stellar black holes, formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities may be the size of an asteroid, but have the mass of a planet. The possibility that Planet 9 is one of these ancient, mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this of course does not completely contradict the impossibility of its detection, since such an object would theoretically be no larger than a basketball. According to another theory, Planet 9 may be a concentrated blob of dark matter. This form of matter, which does not emit, absorb, or reflect light, accounts for a significant portion of the total mass of the universe, but remains one of the greatest mysteries. Dark matter clumps, theoretical clusters of dark matter, are thought to have arisen from density fluctuations in the early universe. As the universe expanded and cooled, these gravitational fluctuations led to the formation of dark matter structures ranging from small clumps to massive halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable using conventional telescopic techniques. The primordial black hole and dark matter clot hypotheses emphasize the profound implications of the search for Planet 9 far beyond the discovery of a new member of the solar system. Whether it's an ordinary planet, a primordial black hole, or a dark matter clot, one way or another we'll find ourselves on the favorable side of events. The search for Planet 9 is a testament to humanity's enduring curiosity and relentless pursuit of the unknown. A recent preprint of a research paper by the same Mike Brown and Konstantin Batygin and their colleague Matthew J. Holman entitled Pan-STARRS 1 Search for Planet 9, dated February 1, 2024, reflects the meticulous ongoing efforts to uncover this enigmatic member of our solar system. The study used extensive data from the Pan-STARRS 1 survey, which, with its deep and wide sky coverage, provided a unique vantage point for the search. By focusing on single-night transients and using a sophisticated Keplerian orbit linking algorithm, the researchers sifted through billions of detected objects, a task akin to finding a single grain of sand among the entire North American coastline. This methodological approach represents a significant leap forward, building on the foundation laid by previous surveys such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 survey, the elusive ninth planet remained out of sight. No features matching the search parameters were found in the data. This result, while not leading to the discovery of a ninth planet, nevertheless narrowed the search area considerably, excluding 78% of the parameter space in which the planet could potentially reside. The remaining 22%, areas with poor observational coverage or inaccessible to current detection capabilities, represent the next frontier in this space search. The journey doesn't end with the PS1 research. The upcoming launch of the Vera C. Rubin Observatory promises to usher in a new era of astronomical observation with capabilities that can finally pierce the veil of mystery, including that which surrounds Planet 9. As we stand on the threshold of these future explorations, the search for Planet 9 remains a beacon of scientific inquiry, a reminder of the vastness of the universe and the small but significant place we occupy in it. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the 9th planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh ratio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a 9th planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, As New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Pallidie, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New Horizons' leap into the unknown bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Pallidie is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, churning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the Sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the ninth planet, has found its relatives among the vast number of Kuiper Belt objects, or KBOS, like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies. Each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kuiper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Arrokoth, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Bennu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, From its discovery to the present day is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the ninth planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe. In the field of space exploration, the James Webb Space Telescope is a beacon of human ingenuity and curiosity. Its recent incursion into the depths of our solar system has revealed discoveries that challenge the possibility of life beyond Earth. Among the many celestial bodies orbiting our giant neighbor Jupiter, Europa is a world of special interest. With its jagged surface and hidden ocean, this icy moon has long intrigued scientists and dreamers alike. However, it's the recent discovery of JWST that's brought Europa into the spotlight of astrobiological research. JWST, in an unprecedented observation of the Moon, has discovered carbon dioxide on Europa's surface. This discovery, while seemingly simple, has profound implications. Carbon dioxide, a molecule integral to life as we know it here on Earth, could be a marker pointing to the potential for life on extraterrestrial worlds. Let us together delve into the data obtained by JWST. What secrets does Europa hide beneath its icy facade? Could the discovery of carbon dioxide be a clue to life beyond Earth? Europa, a moon full of mystery, is a landscape both alien and fascinating. Its surface is covered in a canvas of ice with a complex network of lines and ridges. These features, known as lineae, are not just surface scars, but tell the story of the dynamic geologic processes taking place. This 9 to 15 mile thick ice shell hides a vast ocean that has interested scientists for decades. The lines on Europa's surface are believed to be the result of the ice crust interacting with the moon's underground ocean. These cracks and ridges form as the ice shifts and breaks, a process driven by Europa's motion around Jupiter. Beneath this frozen barrier is a salty ocean, estimated to be 40 to 90 miles deep. This hidden sea, dark and cold, is kept liquid not by solar heat, but by Jupiter's immense gravitational pull. So-called tidal deformations. The satellite rotates around its giant parent and generates enough heat to maintain the ocean's liquid state. The chemical composition of this ocean is the subject of intense research and speculation. It's believed that there may be hydrothermal vents on the ocean floor, similar to those found in Earth's oceans. These vents may provide the necessary energy and minerals to sustain life, making Europa's oceans a prime candidate for the search for extraterrestrial life. The physical properties of Europa's oceans also raise intriguing questions. The presence of salts and the ability to form complex organic compounds, combined with the energy of hydrothermal activity, create an environment in which life can exist. Ocean depths and pressures, although extreme, are not beyond habitability, as evidenced by life in the deep gorges on Earth. Europa's mysterious environment with its icy surface and ocean is an interesting case for research. But what exactly has attracted the eyes of scientists to this moon this time? With the help of JWST, astronomers have made an interesting discovery. Using data from NASA's Space Telescope, they've detected carbon dioxide on the icy surface of the satellite. This discovery is not just an addition to Europa's chemical profile, it's an important key to understanding the moon's potential for life. Using the near-spec near-infrared spectrograph, JWST has discovered carbon dioxide in the geologically young and chaotic Terra Regio locality. This discovery is not just about the presence of a molecule, it's about its origin. The carbon dioxide on the surface of Europa is thought to have come from within, from its mysterious underground ocean, rather than having been deposited by external forces, such as meteorites. This discovery suggests a dynamic exchange between Europa's ocean and its icy shell. The most interesting thing here is that carbon dioxide is unstable on Europa's surface, suggesting constant replenishment from the moon's interior. The presence of carbon dioxide in the young terrain region indicates a recent and possibly ongoing process. This exchange may hold the key to understanding ocean chemistry and, by extension, its ability to support life. This discovery was made possible by the near-spec JWST instrument, which provided detailed spectra of Europa's surface. The ability to pinpoint the location of specific chemicals, such as carbon dioxide, allows astronomers to build a more complete picture of Europa's chemical landscape. Each discovery adds a piece to the puzzle of this mysterious moon. But why is this gas being released? And even more so, how does this cosmic body remain warm, supporting a liquid subsurface ocean? Europa, in its gravitational interaction with Jupiter, experiences a phenomenon known as tidal deformation, or tidal flexing. This process, caused by Jupiter's enormous gravitational pull, is one of the key factors in shaping Europa's potential to harbor life. As Europa revolves around Jupiter, its shape is constantly bending. This constant bending generates significant internal heat, a process quite different from the solar heating that we're familiar with on Earth. This internal heating is critical because it's thought to keep Europa's underground ocean in a liquid state, despite the relatively low temperature of outer space. The heat generated by tidal bends may also stimulate geologic activity on Europa, such as subglacial volcanism and hydrothermal vents. These openings, if present, may be similar to those in Earth's deep oceans, which teem with life despite the lack of sunlight. The energy provided by tidal bends could be a crucial ingredient for life. In Earth's oceans, hydrothermal vents support entire ecosystems where life forms utilize chemical energy released from the Earth's interior. On Europa, a similar process could occur, with life forms potentially using the energy from hydrothermal vents to power their metabolic processes. In such an environment, life could exist independently of sunlight, relying instead on the chemical and thermal energy provided by Europa's internal dynamics. Carbon dioxide, a molecule so integral to life on Earth, now takes center stage in the discussion of extraterrestrial life. On our home planet, carbon dioxide is the cornerstone of the biological process of photosynthesis that drives Earth's ecosystems. But what role can this essential molecule play in the cold, alien environment of Europa? The discovery of carbon dioxide on Europa by the James Webb Space Telescope opens up intriguing possibilities. In extraterrestrial environments, especially on icy moons like Europa, carbon dioxide may play a different but equally important role in sustaining life. In the absence of sunlight, life in Europa's oceans will have to rely on chemical energy, a concept known as chemosynthesis. This is where carbon dioxide can play a key role. In Earth's deep oceans, some organisms use carbon dioxide combined with hydrogen from hydrothermal vents to create organic matter. This process, although independent of sunlight, is a fundamental aspect of life in extreme environments. The presence of carbon dioxide on Europa may indicate a similar process. If there are hydrothermal vents in Europa's oceans, as many scientists believe, these may be the very places where life forms use carbon dioxide, perhaps like Earth's deep-sea organisms. This leads to an intriguing question. Could the carbon dioxide on Europa's surface be a byproduct of biological activity in its oceans? While the topic remains speculative, such a possibility adds an exciting dimension to the search for life beyond Earth. The role of carbon dioxide in extraterrestrial biological processes is the subject of intense research and speculation. Its presence on an icy moon may be a marker indicating the potential for life in environments far removed from the sunlit world we know. So let's summarize. The key to Europa's potential habitability lies in three basic elements: liquid water, an energy source, and the necessary chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa's subsurface ocean and the energy generated by tidal bends are consistent with the first 2 points, and the presence of carbon dioxide on its surface hints at the presence of the necessary elements. Detecting carbon dioxide on Europa is an important piece of the puzzle. On Earth, carbon dioxide is integral to life, playing a central role in photosynthesis and respiration. In the alien environment of Europa, this molecule may be equally important, potentially acting as a building block or part of metabolic processes for hypothetical life forms. The presence of carbon dioxide also suggests that Europa's environment is chemically active, a key factor in the search for life. This activity could indicate geologic processes or even hint at biological processes if life existed there. It's also only possible to emphasize the importance of studying Europa's ocean as a testing ground for understanding the origin of life. The conditions on Europa may be similar to those of early Earth, giving a rough idea of how life could have originated under extreme conditions. On Earth, carbon dioxide is a fundamental component of life, involved in processes such as photosynthesis and respiration. In the alien environment of Europa, this molecule could play a similar role, potentially serving as a building block for life or part of the metabolic processes of a life form. Carbon dioxide could be a byproduct of biological activity or a resource. As we stand on the threshold of a new era in astrobiology, the significance of the discoveries of the James Webb Space Telescope propels us into a future rich with possibilities. Upcoming missions to Europa, particularly the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's Europa Clipper, are designed to broaden our horizons and deepen our understanding of this enigmatic moon. NASA's JUICE mission, launched on April 14, 2023, aims to make detailed observations of Jupiter and its 3 large icy satellites, with a particular focus on Ganymede. However, the Europa survey will provide important data that will complement JWST's findings by providing insight into Europa's icy crust and its subsurface ocean. In turn, NASA's Europa Clipper, scheduled for launch in October 2024, is designed specifically to study Europa. Equipped with a suite of sophisticated instruments, this mission will conduct a detailed reconnaissance of Europa's ice shell and subsurface ocean in search of signs of habitability. The purpose of these missions is to build on JWST's groundbreaking discoveries, delve into the mysteries of Europa's environment. By scrutinizing Europa's surface, analyzing its ocean, and searching for biochemical signatures, these missions will improve our understanding of this moon's potential to support life. By the way, you still have a unique opportunity to be part of this historic exploration and get into the history of this remarkable moon. To quote NASA, join the mission and have your name engraved on NASA's Europa Clipper spacecraft as it travels 1.8 billion miles to explore Europa, an ocean world that may support life. Sign your name today to the message in a bottle. End of quote. Just imagine at a time when some people haven't even visited the next country, a piece of your personal history will travel such distances to orbit another planet. A truly mesmerizing thought. By adding your name, you're not just leaving a personal mark, you're becoming part of a legacy that will resonate in the annals of space exploration. Europa, once a distant and icy moon, is now the center of our quest to understand the existence of life beyond Earth. The JWST results, combined with future JUICE and Europa Clipper studies, usher in a new era of astrobiology. An era in which the search for extraterrestrial life is moving from the realm of speculation to reality. The solar system has served as a reliable bulwark for life. But one day, humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing feature. Life can be found in their interior, many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious, distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system, and, in addition, the search for places where human-like life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets, with a size and conditions similar to Earth's. As of now, we already know about more than 5,500 planets outside the solar system, and the recently sent James Webb Telescope will likely to be able to show us even more distant planets. Further, in 2013, scientists were able to determine the planet's color for the first time, and a year later, they were able to record the magnetic field, and later, volcanic activity. Finally, in 2018, astronomers made a new, potentially breakthrough discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. While this may not seem like such an incredible discovery at first glance, exomoons open a new chapter in modern astronomy, not only as novel, hitherto unexplored space objects, but also as potential elements for supporting life on exoplanets and satellites themselves. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did the scientists manage to confirm so many planets in such a short time, when it's impossible to take a photo of each one? Only 69 planets were found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes by its central star, the same star becomes slightly dimmer, which reveals the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet, and may turn out to be just a glitch, it is currently the most effective of all. Exoplanet exploration plays a crucial role in all of astronomy and the future of all of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are of not much interest to current research. The main problem associated with the search for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult and, to some extent, even impossible task for our current technologies to investigate them. The transit method, or more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet. But a satellite orbiting it? Almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Thus, even the very first exomoon found by Kepler and the ones discovered later near the planets Kepler 1708b and Kepler 1513b are still not perceived as full-fledged proof of their existence, and therefore there is a possibility that it could be just some kind of technical error during the observation, which is not so far from the truth, since further observations did not yield any encouraging results. However, as in the case of the giant planet satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. Such a huge size of a possible moon may become one of the most important elements in the further search for other moons. Thus, more than 20 exomoon candidates are currently known. All of them are gigantic. Probably at least for Kepler 1625b, it's the star around which it orbits. It is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have a very high chance of a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite, when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it is possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets like Earth are still of much higher importance in scientific circles. But we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, or 5,268 kilometers. But recorded exomoons can reach the size of the Earth, or even Neptune. Therefore, since such moons are even difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many of the features of planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future, and that is the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could, hypothetically, be a haven for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere, but also have more access to building chemicals, both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. But the main argument for exomoons as one of the most intriguing places for life to exist is the availability of several heat sources for them. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the interior of the moon in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bringing various crucial chemical elements to the surface. So exomoons are not as simple as they may seem. Perhaps the difficulty of finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. Thus, the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex intelligent life has developed. The Earth, hypothetically, may be almost the only planet on which life could have formed, at least in the visible universe. And any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter of the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is not going away. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method or gravitational lensing will not help to look for microsigns of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. So, if interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human knowledge of the research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Plato mission, which will continuously look at several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this expected discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen what's known about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of bio or even technosignatures created by civilizations on various moons can provide a clearer picture of the signs for the development of intelligent life, thus building more prioritized paths for future missions to the most likely planets or moons for aliens to live on. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and skeptical insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome, mysterious cosmos one day become less confusing to us. But in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcome. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the moon, Io. unlike any other orbiting the mighty Jupiter. Shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close approach is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles, given that the moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable and, interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus or the extended sodium nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the magnetosphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JUICE. JUICE aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JUICE's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JUICE passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JUICE has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JUICE can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the IVO mission is exploring the bowels of the moon. What lies beneath its fiery facade? IVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. IVO observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned, not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. There is a hidden order in the void of space, a subtle force that controls the movements of the celestial bodies with an invisible hand. Far from the chaotic randomness one might expect in the vast cosmos, there is a mysterious harmony, a set of invisible rules that dictate the paths of planets, moons, and asteroids with remarkable precision. Consider for a moment that the giants of our solar system are not just isolated spheres of rock and gas, but participants in a grand gravitational party whose every move is influenced by the forces generated by their cosmic neighbors. Among the actors are Jupiter and its moons. Behind them also lies the asteroid belt, a vast ring of debris that holds voids of mysterious origin. These voids, devoid of the rocky features typically found in the rest of the belt, hint at an unseen participant silently shaping the structure of this cosmic phenomenon. Even distant Neptune and Pluto tell a tale of complex gravitational interaction, locked in such a precise rhythm that their paths never cross. These patterns and rhythms are constantly emerging in the vastness of space, hinting at the underlying order that governs the universe. Orbital resonance is the very concept behind this behavior. What forces act on this mechanism of behavior, both simple and bewilderingly complex at the same time? Let's find out. Behind the facade of the night sky, a complex network of forces operates to dictate the movements of celestial bodies. Gravity, the fundamental force that keeps our feet on Earth, extends far beyond our planet, creating the architecture of the cosmos on a grand scale. At the center of our solar system is the Sun, a colossal furnace of nuclear energy whose gravitational pull subordinates the motions of the planets around it. This gravitational interaction is not a one-way street. Each planet, in turn, exerts its own gravitational pull, creating a complex network of forces that affect their orbits. When two celestial bodies come close together, their gravitational fields interact, influencing each other as if playing a cosmic tug-of-war. This interaction can lead to subtle changes in their trajectories, an effect that's most pronounced in systems with closely rotating bodies, such as Jupiter and its Galilean moons. Consider the case of Jupiter, a giant of the solar system whose massive gravitational field holds a retinue of moons. Among them, the Galilean moons, Io, Europa, and Ganymede, exhibit a remarkable phenomenon known as mean motion resonance. This occurs when the periods of their orbits around Jupiter maintain a constant ratio, a delicate balance that prevents their trajectories from becoming chaotic, despite their close proximity. This gravitational interaction leads to a rhythmic alignment of the moons that repeats over time, ensuring their long-term stability. The forces at work do not simply pull the moons along their trajectories, but push them to positions that minimize potential disruptions to their orbits. Beyond the region of Jupiter and its moons, the gravitational interaction extends to the asteroid belt and beyond, where countless rocky bodies are influenced by the gravitational pull of nearby planets. This interaction can lead to gaps in the asteroid belt, regions devoid of asteroids formed by the resonant effects of Jupiter's gravity. Based on the above, we can conclude that gravity acts as a weaver in the cosmos. Its threads pull and shape the trajectories of celestial bodies, creating a harmonious order out of potential chaos. This gravitational influence, a fundamental aspect of the universe, provides the basis for the interaction of planets, moons, and stars. But is it as easy to understand as it is obvious? In the gravitational embrace of Jupiter, the largest planet in our solar system, there is an amazing example of cosmic harmony, the Laplace resonance. This unique gravitational relationship involves the three previously mentioned major moons of Jupiter, Io, Europa, and Ganymede. Each of these moons, a wondrous world, is involved in a synchronous orbital interaction that has intrigued scientists for centuries. Laplace resonance is characterized by the exact ratio of the orbital periods of these moons. For every 4 orbits that Io completes, Europa orbits twice, and Ganymede completes 1 orbit. Due to this gravitational pattern, the moons align at regular intervals in a pattern that repeats itself every 7 Earth days. Resonance is not just a curious phenomenon. It has profound implications for the moons themselves. Gravitational interactions, especially between Io and Europa, cause significant tidal heating on Io, which promotes volcanic activity. This energy dissipation also affects Europa, potentially contributing to the maintenance of its subsurface ocean. Laplace resonance provides a clear example of how celestial bodies, through mutual gravitational influence, can establish stable and predictable patterns that persist over centuries. But the story doesn't end with satellites alone. Saturn, the jewel of our solar system, is surrounded by a series of mysterious rings. These rings are made up of countless particles of ice and rock, from a speck of dust to a mountain-sized lump. And yet, among this continuously glowing belt are gaps, vast stretches of emptiness that baffle. What had to happen for them to occur? One of these discontinuities, the Cassini separation, is evidence of the forces of orbital resonance. It's not simply a lack of material, but a boundary created by the gravitational influence of Saturn's moon, Mimas. Mimas's role in creating this gap is a fascinating example of orbital resonance in action. Mimas, although small compared to the gas giant around which it orbits, exerts a significant periodic gravitational influence on the particles inside the rings. This effect is not random. It occurs at specific points in the orbits of the particles, because their orbital periods are in resonance with the orbit of Mimas. For every 2 orbits that Mimas makes, the particles at the edge of the ring make 1, thus having a resonance in the ratio 2:1, which leads to repeated gravitational interactions at the same point of the particle's orbits. These repeated interactions have a cumulative effect and act like a cosmic broom, clearing the way and creating the Cassini separation. Particles that once occupied this space were either pushed into new orbits or stuck together to form larger bodies, leaving behind the void that marks the boundary between Saturn's A and B rings. This process is akin to nudging a seesaw at just the right moments. Each nudge adds a little more energy to the system, and in the case of the planet's rings, each gravitational push by Mimas moves the particles around, clearing a path in the rings. However, the influence of Mimas and orbital resonance is not limited to the Cassini separation. Similar resonances caused by Saturn's other moons shape the complex structures of the rings, creating a pattern of discontinuities and dense bands that make the planet's rings dynamic and ever-changing. Between the orbits of Mars and Jupiter lies the asteroid belt, a huge cluster of rocky remnants from the era of the formation of the solar system. However, this region is unevenly filled. There are distinct gaps known as Kirkwood gaps. These gaps are not the result of missing asteroids, but represent areas where Jupiter's gravitational influence has organized stellar clearing. Kirkwood gaps are named after Daniel Kirkwood, who observed in the 19th century that these gaps correspond to orbital resonances with Jupiter. In these resonances, the orbital period of the asteroid in the gap will have a simple ratio to Jupiter's orbital period, such as 1:2, 2:3, or 3:4. At such distances from the Sun, the asteroid's orbit will periodically align with Jupiter in a pattern that will be repeated at each orbit. Over time, these repeated alignments expose the asteroid to regular gravitational jolts from Jupiter, changing its orbit. When an asteroid falls into one of these resonance gaps, repeated gravitational jolts from Jupiter can increase the eccentricity of the asteroid's orbit, putting it on a more elliptical trajectory. This could cause the asteroid to move to a different orbit, leaving the resonance gap-free. To visualize this phenomenon, imagine an asteroid approaching one of these resonant orbits. As it approaches, Jupiter's gravitational pull synchronizes with the asteroid's orbit. If this synchronization falls within the Kirkwood gap, the asteroid experiences repeated pulls, pulling up slightly each time it completes its orbit. Eventually, these jolts can shift the asteroid's orbit, pushing it out of the resonance gap into a less perturbed region, where Jupiter's influence is less synchronized with its orbit. In the outer part of our solar system, beyond the gas giants and the icy Kuiper belt, lies another fascinating story of celestial harmony. Neptune, the 8th planet from the Sun, and Pluto, a dwarf planet in our system that was once considered the 9th, have a unique gravitational relationship that defies the odds of collision. This relationship is determined by the 3:2 resonance gravitational law, which ensures that for every 3 revolutions of Neptune around the Sun, there are 2 revolutions of Pluto. This rhythmic interaction is not just a coincidence. The influence of this resonance is profound, shaping their orbital trajectory so that, despite their overlapping orbits, Neptune and Pluto never collide. Pluto's orbit, influenced by this resonance, is markedly eccentric and tilted as it winds above and below the plane of the solar system, balancing over millennia. This harmonious arrangement emphasizes the complex laws of physics that ensure stability and order in the vastness of space. But what do all these things have in common? The satellites, the planets themselves, their rings and asteroid belts. And why are only some of them affected by orbital resonance? The answer lies in the subtle interplay of celestial mechanics, where eccentricity, inclination, and gravitational forces come together. Orbital resonance is based on three key factors: eccentricity, a measure of the elongation of an orbit; inclination, the tilt of an orbit relative to a reference plane, whether concerning a star or another celestial body; and gravitational forces, which tie everything together. These elements are intertwined, determining whether a body falls into the grip of orbital resonance or avoids it. When a celestial body falls into resonance, its orbit becomes locked in a gravitational interaction with another body, usually a much larger one. This fixation can increase stability, as seen with Neptune and Pluto. However, there are simultaneous exceptions in which objects will be ejected from their trajectories, cutting gaps in regions such as the asteroid belt. The role of eccentricity and tilt in this process cannot be underestimated. A small increase in eccentricity, for example, can dramatically change the gravitational interaction of a body, bringing it into or out of resonance. Similarly, inclination can tilt an orbit so that it interacts with the gravitational influence of another body at just the right point to enter resonance. This complex balance of forces makes orbital resonance a selective phenomenon, affecting only those bodies that meet the precise conditions necessary to synchronize with the rhythm of their larger neighbors. It's a cosmic lottery where the prize is a stable orbit or, in some cases, total expulsion from the system. Looking beyond our solar system, we discover how the action of orbital resonance plays out on a grand cosmic stage, determining the fate of exoplanetary systems across the universe. These distant systems, with their unique clusters of planets, offer a fascinating glimpse into the complex design of the celestial mechanics that govern them. Observations of these distant worlds have revealed cases where the planets keep pace with each other, their orbital periods maintaining an exact relationship. One striking example is the TRAPPIST-1 system, where several Earth-sized planets are locked in a complex chain of resonances. Such configurations raise intriguing questions about the formation and evolution of planetary systems, challenging and refining our theories. Meanwhile, the major planets of the solar system themselves do not show a clear pattern of orbital resonance with each other. Their orbital periods don't have a simple integer ratio that would indicate resonance. While there are close resonances, such as the 5:2 resonance between Jupiter and Saturn, they're not as precise or stable as resonances between some moons, or in more dynamically bound systems such as Pluto and Neptune. The implications of these observations go far beyond simply cataloging celestial phenomena. They provide insight into the processes governing planet formation and suggest that resonances may play a key role in the assembly of planetary systems from protoplanetary disks orbiting young stars. As we continue to observe and study such phenomena, each new study peels away another layer, revealing the intricate plan of the universe, bringing us closer to unraveling the fundamental principles that govern celestial motion and illuminating the very essence of our existence.